So taking the density measurements involves taking a volume measurement. The density actually is a calculated value. So after we weighed the mass, we have a scale there, and that's going to be fairly self-explanatory, and it's a digital readout. Then the volume is where there's a little bit more of an arbitrary or a estimation going on. So looking at this, these are, the thing I'll point out about these, we're looking at a scale between the whole numbers are 3, 4, 5, and then there's evenly spaced 10 markings between them. So they are conclusively giving you those lines, and they represent the first decimal place. So we have 3.1, 3.2, 3.4, or 3.3, 3.4. So the first estimated digit is actually going to be 2 decimal places in. So looking at this first one, the other thing I'll point out is that these pictures, they're a little bit funny. If you look at the way the numbers are displayed, they're not counting upwards as it goes, not as if it's filling, but it's as if it's dispensing. Okay, so there's a 3 and then 4, 5 going downward, counting downward. So this is a specialized piece of glassware called a burette, and it actually releases liquid out to the bottom, and so you actually want to count from the top down, if that makes sense. So looking at letter A, we've got a 3, 4, 5, and then the measurement would actually be around 5.1, probably 2, I would say, estimating, because I'm counting downwards. You kind of have to flip your brain around, but don't let that throw you off. Go ahead and complete the other 3 measurements on your own and see how closely you get to. I jotted down my estimates. Remember that the last digit is just an estimate, so if you're within 1 or 2, you're probably doing pretty good. If the first number or the second number, the first decimal place, if you're off on those, then double check the way that you're reading the scale and that your number is accurate. So the other thing I'll mention with this is that there is a method called the water displacement method to measure volume of solids. Now, this is for irregularly shaped objects, maybe like a key or a crystal or something that's kind of hard to measure with a ruler. And the way that the water displacement method is used is to lower the solid into a liquid solution and then see how much water is moved out of the way by lowering that in there. So if you think of someone taking a bath, getting into the water, it's going to raise the water level by a certain amount. So that method is commonly used. You may use that in your laboratory or something that you can try at home. Then you can determine the density of your key, for example, and then look online for metals and metal alloys and see if you can determine what the key is made out of. You can do that with coins as well. Other metals are a good one to check. Our first real density problem, here we go. A glass mirror fragment had a mass of 7.891 grams and a volume of 2.587 milliliters or cubic centimeters. Those two are used interchangeably. Find its density. So we know the equation for density is mass divided by volume. That's one you want to commit to memory. It's fairly straightforward. Mass divided by volume. So the density is those two numbers. I won't repeat them just for getting tongue-tied here, but those two, the first number divided by the second number, and that comes out to be 3.050. Now the unit that we're going to use is called a mixed unit, and the units didn't go anywhere. The grams still there, the milliliters still there. So the unit for this is 3.050 grams per milliliter, or grams per cubic centimeter would also be just fine. Those are used interchangeably. How many significant figures? This would follow the multiplication and division rule since we're using division. They both have the same number of significant figures, so we're limited to 4 total, and that's what we have in our answer. Your calculator, you may have been tempted to leave off the last 0 and say, oh, well, that didn't tell me anything new. But make sure you include that 0 so that you're accurately representing. You didn't lose any of the accuracy of your measurement. You didn't lose any of the precision. So make sure that you keep those zeros, that 0 on the end, because you need 4 significant figures. Now, if a more complicated sample was brought in, something like a bag of soil that's very heterogeneous, very fine particles, it would be pretty difficult to analyze that using the methods that we have mentioned so far. So we could get a bulk density measurement, but as far as getting specifics enough to match a soil sample with a location, we're probably going to need to look at a couple different methods. The one is called the sink float method, and I alluded to that earlier with if you place oil on water, you can determine is it floating above the water or sinking under the water. So that's called the sink float method, and that would be used for a more complicated sample to see what percentage is floating, what percentage is sinking. And then a density gradient method is also used where you can have a solution that is low density at the top and then high density liquid at the bottom. Typically these are sugar gradients actually. You have a very dense sugar solution and then slightly less, and then liquidy at the top. And you'll put the soil sample in there, and the soil will actually striate itself into these layers where it's the most comfortable, where it is the most accurate density-wise. And then those measurements can be taken to say, well, 80% of it was very heavy, but then 15% was medium and 5% was low density. And then that intricate soil profile can be matched with a specific location. The other thing you can maybe see from the picture just a little bit is that the color is also a part of the matching. That has to do with what organic matter is present in the soil. And whereas the density has more to do with the type of inorganic rocks and minerals that are present in the soil. So I mentioned just kind of the example of 3 layers in the previous slide, but in reality it's going to be closer to something like 9 to 12 layers that they'll actually profile in the soil. And there are devices, there are machines that will do this, but it's also done by hand using a soil sieve, and it's just as accurate as anything else. But as you see in your book, and the example of putting a mob boss behind bars because of being able to match a soil sample using density measurements. So I'll leave you with that thought to go and check out that story about the mob boss that was put behind bars using a soil sample. And I'll leave you with this one review question. Do soils tend to be heterogeneous or homogeneous mixtures? That was from Chapter 1. And just to kind of bring up that information again, don't let it slip away. Are they heterogeneous mixtures or homogeneous mixtures? If you can't remember right away, go back and check your notes. It's a good time to review Chapter 1. And we will see you next week.